Okay, so welcome back. Now we're going to keep going beyond our own galaxy, and we're going to talk about what we know of other galaxies, the zoo of galaxies, if you will. We see many different types, and we want to try to start to understand them. Where do they come from? Why do they look the way they do? How do they change? How can we categorize them? All those good things. So to start, by the early 1900s, people had noticed and categorized many things that at the time were all called nebulae or nebulas. And so some of these were things that we would still call nebulae today. So things like the Orion Nebula, which is a gaseous, dusty molecular cloud where stars are forming. So that's sort of what we would now call a nebula. Some of these things, it turns out, were just star clusters. Now, sometimes star clusters, especially the younger ones, can be within a nebula. That's where they're being formed, so it makes sense for there to be a few of them. But other times, star clusters can just look like a similar kind of smudge in the sky, and so it was hard to distinguish. So a few of these things had been sorted out what they were. But around the early 1900s, this is when Edwin Hubble, who we'll talk more about as we go through this chapter, was actually able to measure the distances to some of these things that they at the time called nebula. And in particular, he measured the distance to this object M31, which is a catalog code for the what we now call the Andromeda Galaxy. And he used Cepheid variable stars. And what he found was pretty crazy. He found that this object was over 900,000 light years away. So super, super far. Remember, the diameter of our galaxy, the Milky Way, was found a little bit earlier to be about 100,000 light years across. So this is 9 times farther away than that. And it turns out the Andromeda Galaxy is actually pretty close. It's our closest neighbor large galaxy. But at the time, this was by far the largest distance ever measured. And there's a famous story that Hubble, when he presented this work, got a standing ovation from the crowd. Everyone was so impressed with the ability to measure something so far away. And so if it were to be visible from this far away, what that's telling us is there has to be a lot of starlight coming from this galaxy, and it's on the order of 100 billion stars or so. But when we look at it in the night sky, it just looks like a little smudge. Basically, all this light is spread out over the angular size of the galaxy. So that was our first confirmation. But these days, we've seen quite a few galaxies. So this is the Hubble Deep Field photograph, one of the most beautiful pictures, what you get when you point a powerful telescope at the night sky and somewhere very dark where there aren't many stars from our perspective. And what we see is just this endless bounty of galaxies. And when you look at this picture, you'll see that some of them you can kind of see a spiral shape too, or some of them look like streaks or lines, while others are more like a blob. They come in a bunch of different colors, different sizes, and also different shapes. And so, when you have some system like this, where you have a bunch of new objects, a good place to start is just to try to categorize them, like just to sort them, like what kinds of things do you have? And then from there, you can try to explain how maybe each type might form. You can start to find the similarities and differences, but we want to start off with classification. Now, before we start classifying galaxies, we want to remember that we're seeing objects that are 3D objects, but we're only seeing them from one angle. Okay, so it's like the famous story of a bunch of blind people touching an elephant, and one of them touches the trunk and thinks it's a snake, one of them touches the leg and thinks it's a tree, one of them touches the tail and thinks that it's, I don't know, a paintbrush or something. Depending on where the galaxy is, how it's angled relative to you, it can look quite different. And you can kind of see that in this picture, but we need to keep it in mind as we go on to classify these faraway galaxies. Okay, so what are the first type of classification that we should talk about? Well, they're the ones we already saw a little bit. The one that the Milky Way is a part of. These are spiral galaxies. So spiral galaxies make up about half of the larger galaxies, maybe a little more. Depends on what your cutoff size is. Um, and what they have in common is that they have a flat disk, like a CD, with these spiral arms, and they have a bulge in the center. Okay, so in those spiral arms, that's where we have typically a lot of dust. That's where we have molecular clouds. There's new star formation happening. And this is just like the Milky Way, right? In the Milky Way, we also have a bar in the center. And so that bar structure, some spiral galaxies have them and some don't. So we'll see in a moment, but we basically have two buckets that we can sort these into: spirals with bars and spirals without bars. We can also use some of the modern tools of astronomy to try to understand what's happening with this distinction. And what we find is that basically about half of spiral galaxies have a bar, and it seems to be a long-lived stage in their development where maybe before they don't have one and maybe later they don't have one, but for a big chunk of their lifespan they have this structure. The particular shapes and structures and sort of the number of arms and how tightly wound up they are, that's something that varies within spirals. Now, it's good to have some vocab here. When we see the picture on the right, we call this a face-on view. We're looking at the flat side of the galaxy from our perspective. The picture on the left, we call that an edge-on view. We're looking at the edge that causes our galaxy to just look like a diagonal little streak. Okay, so if we go back to the deep field photograph, you can see in this, if you start looking closely, some little streaks of light. Those are edge-on spiral galaxies, or at least very flat galaxies. We also see some face-on spiral galaxies. They're the ones that are very beautiful, where you can see the arms, like this one at the top here. And then most of the time we find them somewhere in between, right? Kind of at some sort of angle to us. Okay, in addition though, we have a new type of galaxy we should talk about, which we kind of saw a little bit of in the last chapter, which these are elliptical galaxies. So they're pretty rare to be big galaxies, only about 15% of the big ones, but they're about 80% of all galaxies, because most, similar to stars, most galaxies are pretty small. And so a large fraction of the small galaxies are elliptical. That includes what we call dwarf elliptical galaxies. An example of that was the one we discussed last time that is being pulled apart by the Milky Way as a satellite galaxy. Now, within these elliptical galaxies, they're basically big balls of stars. They tend to be older stars, population 2 stars. And these galaxies are kind of like globular clusters, but they're much bigger. Even the small ones are maybe thousands of globular clusters in size. They often actually contain globular clusters themselves, so we can have both at once. Now, within elliptical galaxies, stars are going to rotate not just in one direction, but in all sorts of different orbits at different angles, and also in different directions within that. So the motion is much more random seeming. They haven't had time to interact really, or we'll talk about their formation in a moment, but basically they haven't been able to flatten into a disk, which is what would happen if there were ways for them to interact and cancel out the stray directions of angular momentum. Because of the random motions, it's hard to measure the mass of them. We have to apply some different techniques. But we know that the biggest elliptical galaxies have masses that are just ridiculous, much bigger than the largest spiral galaxies. So these are very rare, but we have found elliptical galaxies up to 10 trillion solar masses, which is ridiculous, okay? Much bigger than the Milky Way. Okay, and then our catch-all category, the weird ones, we have what are called irregular galaxies. And irregular galaxies are basically, for the most part, a result of something violent, something chaotic happening. And that typically means merger or collision. So in the top here, we have an irregular galaxy, which you can probably tell is really just two galaxies in the process of colliding, ripping each other apart. In this bottom picture here, this is, I believe, from Chile. So it's showing the southern hemisphere sky, which is different than what we see in the northern hemisphere. And you'll notice on the left, there are two white splotches, a big one towards the bottom and a smaller one higher up. Those are the Magellanic Clouds. And they're not really clouds, they're actually small galaxies, satellite galaxies of the Milky Way. They are irregular galaxies, again, because they're being pulled apart by, in this case, by our galaxy, the Milky Way. So there aren't very many irregular galaxies, but they're very interesting objects to study because they tell us a lot about the ways in which stars interact, the ways in which gravity works in these really complex systems. And we can simulate these with supercomputers and try to understand both what we see and the invisible part, right? Like the dark matter, this part of the dynamic. So they're very useful and interesting objects. Now, putting this together, we have what's known as the Hubble classification, again, named after Edwin Hubble, the person who figured out that some of these smudges are actually very, very far away galaxies. Now, you'll also hear this called the tuning fork model because it looks kind of like a tuning fork with two prongs on the right and a handle on the left. So the handle, those are the elliptical galaxies. And basically, we see that on the left, we have a spherical elliptical galaxy. That's an E0. And then as we go to the right, we get more and more elongated elliptical galaxies until we get to an E7, which is a really elongated, flattened elliptical galaxy. But it's still a big ball. Now, in the middle, S0, these are what we call lenticular galaxies. So this is actually a different kind that we haven't seen so far. They're kind of like the in-between. So they are flat, like a spiral galaxy, and they have a bulge like a spiral galaxy, but they don't have any arms. So they're armless, which is similar to an elliptical galaxy. So these lenticular, this is what's in between. And then you can see the top branch, these are the spiral galaxies, SA, B, and C. And basically SA, that's where we just have the two primary arms. SB is where we start to have some more wound up structure. And SC is a really tightly wound galaxy with lots of arms. The bottom, the SBs, work the same way, but these have a bar. So the B is for bar. So these are barred spiral galaxies, and they go from more loosely wound, smaller number of arms, SBA, all the way to SBC, which is more tightly wound. Now, it's important to remember this is not an evolutionary path, just like the HR diagram when we talked about the main sequence. Remember, the main sequence doesn't tell us how a star changes. It just says that when we form a star, depending on its mass, it'll just end up somewhere on the main sequence. Galaxies work similarly. This isn't telling us how the galaxies change over time. When we form a galaxy, for various reasons, it'll end up in one of these places. Okay, so to understand where it ends up, now is a good time to talk about how it changes. So, if it's not just the tuning fork that's the change, how does it change? Well, it depends on the type of galaxy. So what you should think about is if we go back to the galaxy formation discussion we had, galaxies we have a big dark matter ball, a dark matter halo, and then material falls into it. If that material is able to interact before it starts to form stars, then it'll be able to collapse down, cancel out the straight angular momentum directions, and form a disk. And at that point, you either get a lenticular or a spiral galaxy. And then the bar maybe forms at some point due to complicated dynamics. However, if it forms the stars and before it starts to collapse and interact, then that will become an elliptical galaxy. So this is why they tend to have much older stars. They've already undergone formation long ago. The larger ones have died. Now, once we get one of these, they sometimes can turn into the other. So spiral galaxies, they can over time become lenticular. And so what's happening there is over time, the arms are kind of smoothing out and you just get a disk. And that can happen, again, due to some complicated dynamics with gravity. We can also have spirals become elliptical galaxies. That's actually what's going to happen in the future for the Milky Way. So remember, the Milky Way and the Andromeda are on a collision course, these two beautiful spiral galaxies. But as they collide, they're going to rip each other apart chaotically until they become a big ball of stars. That's another way to get an elliptical galaxy, and that's what we believe is the origin of these really, really big elliptical galaxies, is that they come from the merger of multiple spiral galaxies. Um, Now, ellipticals very rarely become spirals. It requires them to somehow get to suck up a bunch of new gas to start causing collisions, which are going to allow for this object to flatten out. So it's pretty unusual for it to happen the other way. But spirals, they just need to collide strongly enough and they'll become ellipticals. Now, while those collisions are happening, remember those are the irregular galaxies. So I didn't mention it, but the irregular galaxies, right, we don't have them in this classification. Sometimes people put them off on their own in a little island. But in reality, they're just the mergers typically of these normal types of galaxies with each other. So we don't necessarily need a different category for them if we keep that in mind. Okay, now when we look at a galaxy, we can also classify it to some extent based on the amount of mass in it compared to the amount of light that it emits. So if we look at our sun, which is just one star, we can define a mass to light ratio, which we take to be 1. So this is just a definition we choose, that if something looks like our sun, it has a mass to light ratio of 1. Now, a lower mass star has less mass, but it has a lot less light that it makes. The lower mass stars have a larger mass to light ratio. It's a little confusing. But remember, most stars are small, most stars are low mass. And so it's pretty common, especially for older populations, to find a larger mass to light ratio. So for example, when we look at a galaxy which has a bunch of stars, we can kind of take the average mass to light ratio to try to understand and classify a galaxy. And the more star formation it is that's happening, the more large stars there will be. Large stars cause a small mass to light ratio. So in the sort of active spiral galaxies making new stars, we get a ratio of maybe between 1 and 10. And that's what we see in this picture here. So this picture on the right is a graph sorting a bunch of sort of younger galaxies based on their mass to light ratio on the y-axis and then their type, their classification on the x-axis. These are sub-classifications within spirals. Now, older galaxies, the big stars will have already died. Remember, the big stars die fast. So all they have left are small stars, which causes the mass to light ratio to increase. And so for ellipticals, for example, we typically find mass to light ratios from 10 to 20. And once we get to the smaller, the dwarf spheroid ellipticals, we can get mass to light ratios up to maybe 1,000. That would be pretty extreme. At that point, we only have the very oldest tiny stars remaining, the ones that live the longest. And so we can use this as just another tool to help us to classify galaxies. And you'll often hear astronomers talking about the mass to light ratios if they're doing some work on galactic, physics. Okay, so now we want to back up a second. We already mentioned how Hubble was able to find, Edwin Hubble, the person, was able to find that galaxies are very far away. So how did he do it? How did he measure these extragalactic distances? Well, again, we're going to rely on the distance ladder. So we're going to start with the things that we know how to do, notably variable stars. And then we're actually going to see some new tools today that help us measure these really, really far distances a little bit more easily. But it's important that anytime we use the distance ladder, we should always keep in mind that it's based on every rung beneath it, right? When you climb a ladder, you have to use the lower rungs to get to the higher rungs. And that's how measuring distance in space works. We use the close things like radar and parallax to calibrate the farther things like variable stars and HR distance measurements and what the things that we'll see today. Okay. So nowadays, with modern techniques, we can measure distances basically as far as we can see. So billions of light years away. which is about the size of the observable universe, all the light that's been able to reach us in the time the universe has existed and been transparent. Okay, so how does this work with variable stars? Well, remember, the way a variable star helps us understand the distance, a variable star is one that flashes. It's bright and then dim, bright and then dim. We can see that in this picture here. So this variable star is in the middle of this small picture. So the bottom picture is what you would actually see if you looked at a big galaxy. We're really going to zoom in. It gets really pixelated, but we see in the left top this little smudge in the middle, and then it gets brighter and then brighter. And then it's going to start to dim. And what we do is we measure how long that takes. Now, you can imagine it's very annoying to do this. So Edwin Hubble, this was a big part of his career. He spent 18 years doing this, and he only found 40 variable stars that he could use in the Andromeda Galaxy. And it turns out around the time of Hubble, people realized that there are actually two different types of Cepheid stars that have slightly different rates at which they pulse. And remember, the pulse rate, that tells you something about the size of the star, how much light it's making. And then we can measure the light we see, and we can compare those to get the distance, how much light it's making versus what we see. That ratio is going to tell us how far away this object is. Right, the farther away it is, it's going to look more and more dim. And so once we use the carefully found two types of Cepheids, we actually found that galaxies were about twice as far as Edwin Hubble first thought. But it doesn't change the story too much. It's just, these are the kinds of details in astronomy. It's a living body of knowledge. We're constantly adjusting things as we get more information. Now, this is a fun connection you might not have known, but you can now see the Hubble Space Telescope. Who is it named after? It's named after Edwin Hubble, this guy who figured out how far away the galaxies are. And what was the main job of the Hubble Space Telescope? Well, one of its main jobs was to do exactly this, to keep doing Hubble's work, to find these variable stars in distant galaxies so we can figure out how far away they are. And the HST did a great job of this. It found lots and lots more variable stars than we had found from ground-based observation. And that's a big part of how we've been able to measure out to galaxies, which then help us to calibrate our next tool. So what is our next tool? Well, these are so-called standard candles. So again, we want to find things where we know how bright they actually are. So when we see them and they look dimmer, we can take the ratio and figure out how far away they are. And so one thing like this is a supernova. So a supernova, depending on the type of star that blows up and depending on, what we see coming from it, that can determine how bright it is if we were up close. There's a very nice relationship. We can carefully do the physics here. And so we should be careful. Supernovae are calibratable standard candles. So not every supernova is like the same brightness. Some are brighter than others based on the mass of the star mostly, but also a little bit of its composition and what's nearby and so on. But we can use all of our tools, all of our astrophysics knowledge to constrain how bright a particular one should be based on what we can observe. And once we get that, we can figure out how far away it is. So we add another layer to the distance ladder. But in order to calibrate these, we need to measure some that are up close. And to do that, we use these other methods like variable stars. So we're still building. As we get more information and new tools, we can go farther in the universe, measuring distances, but we still are relying on everything that came before. Okay, so then in addition to standard candles like the supernovae, we can also use sort of a standard candle via the Thule-Fisher mechanism. So the Thule-Fisher relationship is it's an empirical relationship. So it doesn't have an obvious derivation, at least that wasn't how it was originally found. Basically, what astronomers noticed are that certain types of galaxies, especially spiral and lenticular galaxies, the faster they spin, the more mass they have. And the more mass they have, the more light they emit. So basically, there's this relationship here. You can see we have mass on the x-axis, and we have magnitude on the x-axis, and we have speed on the y-axis, and these two things are related to each other. So we can figure out the absolute magnitude, how bright the galaxy actually is, by measuring how fast it's rotating. It's not a perfect relationship. You can see it's kind of scattered here, but there is clearly some trend line. It gets better if we use the specific type of galaxy here. And so doing that, once we know the absolute magnitude, we can then take what we measure and get a distance. So same kind of deal. Now these look like straight lines, but the x and y axes are actually scaled in a complicated way. So these are logarithmic axes. And so this is really like we call it a power law in astronomy. It's like magnitude or luminosity to some power, to some exponent, goes like the velocity goes to the velocity. So this is a tool, a trick we use in astronomy to make things into straight lines when they're actually curves. And here the slope is going to tell you basically what power you want to use when you write this as an equation. So mathematically, it's a little tricky. We're not going to worry about that too much in this class. But if you were to go on to do astronomy, this is the kind of thing that you spend a lot of time learning how to do carefully. And maybe you have some computer programs that can also help you in your analysis as well. Okay, so there's one more method that we have related to the distance ladder, and this is going to kind of give us a transition into our next set of topics, which have to do with looking at the universe as a whole, the big picture, looking at what's happening at the largest scales. So where this begins is in around the year 1900 with this man, Vesto Slipher. And he was working at Lowell Observatory, which is still functional. It's actually a place where a few of my friends work. And Lowell, the person it's named after, was a really eccentric, wealthy guy back in the early 1900s. He was a millionaire, and he wanted to find aliens. That was what he was interested in. He was hoping that we could use spectra, which is a real tool, to find like Martians or something. So technically, he wasn't that far off. We do use spectra to look for signs of life, but the particular ideas he had about what this might be like and where to look were a little bit wacky. But regardless, he tasked Slipher with basically getting the spectra of galaxies and figuring out what was present, what elements were there. And so in order to do this was very hard. So I don't know if we've discussed it in detail, but to make a spectrum, you have to collect a lot of light because you're going to split that light into different colors, and you need each color to be bright enough that you can see. So, if you can just barely make out a galaxy by squinting in a telescope, you're not going to have enough light to turn that into a rainbow, into a spectrum. What you have to do is you have to split the light and aim it at back in the day, a photographic plate, like a piece of material with some chemicals on it to take a picture. And they would have to leave it aimed at the galaxy perfectly without moving it much for over 40 hours. So they would have to do it all night, keeping it aimed at one object, and then cover it up, and then open it back and do it for another night, and do that for weeks at a time. So you can see how it took quite a while. It took Slipher 20 years of work to get the spectra of around 40 galaxies. Okay, a lot of effort. But what he found was truly revolutionary. It changed our understanding of the world around us. So I think it was worth the effort. What he found is that all of these galaxies were moving away from us. All of them were redshifted. Okay, so what that looks like is when we see the spectrum, there are certain features in it. Like we know sodium has two spectral lines right next to each other, and we see those lines are, more in the red direction at longer wavelengths. Both of them move together. The whole spectrum moves together. It was redshifted. And so that feels really weird, right? It feels disconcerting, this idea that everyone in the universe, all these faraway galaxies, they're not just kind of randomly moving, or they're not just kind of floating there. No, they're all moving away. They're all running away from us. How odd. So how can we understand this? Well, we're going to talk a little bit about it today, but we'll come back to it when we get into cosmology in more detail. So following up on Sleeper's work, Edwin Hubble, a lover of galaxies, wanted to do this even more carefully. So what he did was he used these redshift measurements to figure out the velocity of the galaxies, how fast they were moving away from us. And then he also measured how far away these galaxies were using mostly variable stars, looking at Cepheid variables of the different kinds and determining their distance, the distance to those galaxies that they were within. And what he found is pretty crazy. He found that they formed a straight line, and not just like a power law log graph straight line, but really a straight line. Basically, this is, the distance is the x variable, the velocity away of the galaxy is the y variable, and there's just some number, the slope, where if we do x times y, we get, x times the slope, we get y. And he called the slope h sub 0, or other people did at least. It's now known as Hubble's constant, or Hubble's rate. And what this does is it gives us a new tool to understand the universe, to understand the fact that basically the farther away we look, the faster the galaxies are moving away from us. So Andromeda is actually moving towards us because it's close enough that the gravity of our galaxy, we're being pulled together. But when we look at farther away galaxies, they're moving away. When we look at even farther away galaxies, they're moving away faster and faster. Okay, crazy stuff, right? So we call this observation Hubble's law in honor of Edwin Hubble. And that number, the slope, turns out to be 70 if we use units of kilometers per second per megaparsec, which are pretty weird units. Now, it's actually pretty tricky to get that number, the slope, and we still don't agree actually in physics exactly what it is. So there's something called the Hubble tension, which is that we get two different values for it depending on how we measure it, and it's an active area of research. It's exciting stuff. But what this means practically is that if we see a galaxy that's 1 megaparsec away, a megaparsec is 1,000,000 parsecs. Remember, a parsec is a little over 3 light years. So this is like over 3 million light years away, pretty far away. Remember, our galaxy's diameter is about 100,000 or 0.1 million light years. So 0.1 versus, versus 3 is pretty big difference. These are reasonably close galaxies, but far, in terms of any normal measure. So those will be moving away at 70 kilometers per second. 1 times 70 is 70. If we had a galaxy 100 megaparsecs away, then 100 times 70 is 7,000. It'll be moving away from us at about 7,000 kilometers per second. So that's how we use Hubble's law. This is a kind of calculation I hope that you'll be able to do since it's pretty straightforward. And it's kind of miraculous that the universe works in such a nice, simple way. Now, of course, whenever something is simple, it usually, if we try to dig deeper, it gets a little complicated. So it turns out it's not quite a straight line. So if we look at Hubble's law, that slope, when we look back farther and farther into the past, so if we look at galaxies that are very distant from us, that slope used to be bigger. Okay, so basically that function used to cause distances that are larger to be at higher velocity, and it's slowly decreased. So this is a rough plot of what that looks like. This is still, again, an active area of research. We haven't quite figured out exactly what this looks like. And indeed, you'll see here that this Hubble constant appears to be flattening out, seems to be going to a relatively constant value. So depending on exactly what material is in the universe, and there's still some mysterious stuff out there. So one thing that we call dark energy that may or may not be related to dark matter. So the dark energy, depending on what it is made of, which we don't yet know, that'll determine what happens with this Hubble rate over time. So if the dark energy is a very simple thing, then it'll eventually, the Hubble rate will go to 55 instead of 70. But we actually have very recent data from this year that it seems like this isn't the case, that it's actually something a little bit more complicated, which is going to cause the Hubble rate to continue decreasing forever. Now, confusingly, just because the Hubble rate is decreasing, that doesn't actually tell us how our universe is changing. The Hubble rate is basically the rate of change divided by the thing itself. So even if it's constant, it can actually still be the case that it's expanding faster and faster, if you will. We'll come back to this in a later chapter when we talk about cosmology in more detail. But for now, what do we make of Hubble's law? Well, it's telling us that the universe is expanding. So, when we see everything moving away from us, you might think, wait a second, were the ancient people right? Are we at the center of the universe? No, sadly, we're not. As far as anyone can tell, the universe doesn't have a center. We'll see why that seems to be the case a little bit later. But if you imagine taking a ruler and stretching it out as an ant walks along it, what'll happen is the ant, will experience these longer and longer distances. And so if that ant were a light wave, it would be stretched out. This is the redshift that we observe. So as the galaxies move away, they're not really moving away. What's happening is the distance, this empty space in between the galaxies, is expanding. It's getting bigger. So any region like the galaxies themselves that has gravitationally bound objects, that's not changing in size. So like the distance between the Earth and the Sun, that's not changing in size. The distance between the Sun and the center of our galaxy, that's not changing. But the distances between galaxies that are separated by empty space, that is expanding. That space-time is changing. Okay. We can also think about this like if you have a bread with some raisins in it or something, that basically as the bread bakes, the empty space, or in this case of the bread, the flour mixture, the dough, is going to expand, fills with air, but the raisins themselves don't change in size. They stay the same. They're like our galaxies. And no matter which raisin you choose, you would see all the other raisins moving away from you. So if you choose this raisin, you would see as the bread expands, everything's moving away from you. But if you chose this raisin over here, you would see the same thing. As the bread expands, everything's moving away from you. So this is our current understanding of Hubble's law, is that we see things all moving away from us because of the way that the universe is expanding. We're not at the center. We are just one piece in a much bigger puzzle. And so that's Hubble's law for now. We're going to come back and see it again, like I said, when we talk about cosmology. But for this lecture, I'm going to leave it here, and I'll catch you in the next one.